Hello, my name is Nolan Coulter. This is my first semester here at Wayne State, and I am a computer science major. So while I was browsing through the Scientific American for an article to summarize for Project 1B, I came across Algorithms for Quantum Computers, written by Alan Aspero Guzik. This sparked my interest because I am currently learning about programming and computers through my computer science degree. The two types of computers to know about for this article are quantum computers and conventional computers. Conventional computers are like the one that I'm using right now, that most people have used daily. And then the other, quantum computers, is used for heavy sets of data to make a lot of calculations simultaneously. Each have units that they make their calculations with. The conventional computer uses bits, which either have a value of 0 or 1, whereas quantum computers use qubits, and these can be both 0 and 1 simultaneously. Quantum computers also have an entanglement feature, which helps fix any problems that arise, and it's very useful for entire class problems. Although entanglement helps out a lot with these quantum computers, it does not protect them from an issue called decoherence. Decoherence disrupts a quantum computer's function, which can be very tricky. There has been a lot of research and investigation in how to prevent this decoherence and how to fix it. And researchers have come up with this fixed solution called quantum error correction. But this is only able to happen if the quantum computer contains thousands of qubits inside for its calculations. This becomes a problem though, because the current largest quantum computers, which are named noisy intermediate scale quantum computers, we'll abbreviate that with NISQs, contain only a number of tens of quantum bits. So that's a long way off from the thousands needed to use this quantum error correction. Recently, there has been an increase in NISQ machine use and access worldwide. So this, of course, means that there has been an increase in the research being used on these NISQ machines and how to better them and create more worthwhile programs. There are two heavy focused areas of these algorithm fields that are worthwhile in research. They are simulations and machine learning. Theoretical physicist Richard Feynman stated that the most powerful use of the quantum computer will be the simulation of nature. This means simulating things such as atoms, molecules, and materials. These algorithms used to simulate the physical matter that make up our world can be very helpful in understanding new designs that can be used to increase our energy and make contributions to things such as public health. Machine learning, on the other hand, is something that the computers learn to do on their own through data sets and or experience. This includes clustering items or features that have similarities together without the user having to do much at all, and classifying information by categories, or generating new statistics from existing ones. So looking ahead into the future, there is currently no proof of these quantum computers being more powerful than conventional computers, but as research goes on and people are getting more access to them, there will be an increase in construction of these quantum computers being built larger and capable of more processing, And eventually this will lead to the machines that contain thousands of qubits, which will then bring out the quantum error correction, which is hopefully not too far away. Thank you for listening. All right.